So nodal analysis and mesh analysis have been useful for solving circuits, linear circuits specifically, and in such we end up being able to find every voltage across every element and every current through every element in each problem. It's a powerful technique, powerful two techniques. However, sometimes it's useful to transform one type of circuit of arbitrary level of complexity into another in order to simplify. So take this circuit as an example. We have 7 resistors plus a load resistor RL, at which the voltage V naught appears across it. Suppose I ask you to measure or determine the output voltage V naught for 10 different values of RL. So in this case, would you set up nodal equations 1, 2, 3, and solve that full set of nodal equations each time to find the value of RL? Or would you instead we could create a simpler but equivalent circuit according to RL that behaves the same way, and much quicker solve for the effect on the output parameter of interest. So we're going to transform this circuit shown in black up on the top with 7 resistors into an equivalent circuit where it's being driven by V equivalent in series with an equivalent resistance R equivalent, such that it behaves the same way according to RL. As far as the resistor RL is concerned, these two circuits are no different. Source transformations are one such technique to facilitate this transformation. It's going to allow us to convert a voltage source in series with an element, an impedance, to a current source in parallel with an impedance, or vice versa, such that the output terminals of interest see identical behavior. So let's examine the voltage source in series with a resistor in this case. Since this is an open circuit, the voltage between nodes A and B in this case will be voltage Vs, and that's because there is 0 current going through Rs. So on the right side, what we see is current Is will be going through the resistor Rs, which is in parallel with it. So Is will be going through that, dropping a voltage across Rs. In order to get the equivalent voltage Vs between A and B, Vs must equal Is times Rs. In other words, the current source required just simply equals the original voltage source divided by the resistance. So note, what's happening inside this circuit is not the same, but according to an A and B, when open circuited, you still observe the voltage Vs between the nodes. Now let's examine the response of these two circuits with a load resistance attached between terminals A and B. So first, the voltage source in series with a resistor Rs, now attached to a load resistor RL, such that we have a closed circuit. Now that we have a closed circuit, I'm going to draw the original circuit here in this dotted line. Now that we have a closed circuit, we're going to have current that's non-zero going through it. We'll call that current IL as it's going through the load. And we're going to get some voltage V0 dropped across it. So we can see that based on a voltage division, V0 can be expressed as Vs times the load resistance over the sum of the resistors, Rs plus RL. Okay, and for the opposing case, where we have a current source in parallel with a resistor, that is a resistor Rs, and we're going to attach the same load resistor RL. So in the former case, we had current Is going through Rs. Now Is is being split between two parallel resistors, so we will get a different current IL, which will drop a voltage V0 across it. So let's examine this. We see that capital IL can be described with current division as being a portion of Is given as Rs divided by RS plus RL. Note that IL can be re-expressed as V0 divided by RL from Ohm's law, which equals IS times RS over RS plus RL. Therefore, V0 is equal to IS times RL times, V0 can be expressed as IS times RS times the quantity RL over RS plus RL. This was written in this form such that we can compare it to the case with a voltage source. And from this, in order for them to be equivalent in voltage, we see that Vs must equal Is times Rs, or in other words, Is is Vs over Rs. And if so, then these two circuits behave equivalently, whether it's in open or closed form. So in open form, we see voltage Vs appearing between nodes A and B, and in closed circuit, we drop voltage V0 across RL, given as either of these expressions, and the resistor draws current IL. A couple things to note here. In both cases, we see that the current through the load is given as V0 over RL. It's the same. Second, the voltage or the current inside the black box doesn't have to be equivalent. What we've drawn inside the dotted lines over here is not the same thing as what we drew inside the dotted lines here. Only what we see between A and B through the load has to be the same. And then finally, note that this method cannot be used on dependent sources. Okay, let's see how this works. Let's use source transformation and equivalent resistance to find the voltage V0 in this circuit. Note, this is not an efficient method for solving problems, but these source transformations can be useful in targeted senses. We're just going to use this as an example to illustrate how it works and to prove that we can take a circuit of arbitrary complexity and reduce it down into equivalent, such that seen by this final value, this final nodes that I'm highlighting in red here, the behavior is going to be equivalent. So a quick side note, we see at the very beginning that we have a 250 volt source in parallel with a 125 ohm resistor. The voltage across this 125 volt resistor is merely 250 volts. So this 125 volt resistor is doing nothing to change the voltage potential between these two X's. Therefore, according to the rest of the problem, on the right side of these dotted lines, the current through the 125 ohm resistor is irrelevant, okay, because the voltage potential as seen by everything else is going to be identical. So we can, according to the 100 ohm resistor and where V0 is appearing, the current through the 125 ohm resistor is irrelevant, so we can get rid of it. Likewise, the 8 amp current source in series with a 10 ohm resistor doesn't change the fact that the branch between the points that I've labeled Y here is no different. The 10 ohm resistor does nothing to restrict the current because it's forced by a current source. So we can redraw that as a single current source, and it's going to have no impact on the equivalence the rest of the circuit. So simplifying the circuit a little bit already, we get 250 volts in series with 25 ohms. We have an 8 amp source that's in parallel with 100 ohms, then attached to two resistors that are in series with one another, 5 and 15 ohms. V0 appears right there. So here we can see a few things that we can combine right away. 5 ohms and 15 ohms are in series. That would be 20 ohms. Redrawing the circuit one more time. We get this. Note that now that I've combined the 5 and the 15 ohm resistors into a 20 ohm resistors, I see that the 100 ohm resistor is in parallel with that 20 ohm resistor. Since they're in parallel, voltage V0 appears across both of them. Since it appears across both of them, I can combine those resistors into a single equivalent resistance. When I do that, 100 ohms in parallel with 20 is 16.67 ohms. So our reduced circuit so far looks like this. 250 volts in series with 25 ohms, and we have an 8 amp source in parallel with a 16.67 resistor where V0 is appearing across it. Okay, so now we want to find V0. So we don't want to, we see that we have a current source in parallel with a resistor. That is an indicator that we can do a transformation there, but we don't want to do the transformation here because we're going to lose where the potential V0 is appearing. But we do have a voltage source in series with a resistor. That's also a candidate for source transformation. So this can be transformed into a current source in parallel with a resistor. In doing so, we're going to put the 25 ohm resistor in parallel with the current source, and that current source is going to be valued at the voltage, 250 volts, divided by the resistance, 25 ohms, which is going to be 10 amps. Drawing the remainder of the circuit, we get an 8 amp source in parallel with a 16.67 ohm resistor where voltage V0 is appearing across it. Okay, now we see that every element is in parallel with one another, so we can do combinations of all of these elements and not affect potential V0. So I've got a current source, two current sources, they can be summed together to a final equivalent circuit. Current source, if I choose the direction of current going up, it's going to be given as 10 amps minus 8 amps for 2 amps, going from bottom to top. I have a 25 ohm resistor in parallel with 16.6 ohms, which is going to give us 10 ohms, and V0 is appearing across all of them. Now the circuit is in its simplest form, and we can find that V0 is just simply going to be 2 amps times 10 ohms for 20 volts. Okay, so as you saw, we took many steps to keep reducing the circuit down until we got it into an equivalent form such that according to the voltage V0, the circuit behaved in an identical fashion. Note, we removed a whole lot of details about this circuit. So if we were interested in the current going through the original 25 ohm resistor, we've lost that ability to find because we have combined all of our elements until we could figure out the most simplest form according to the output potential desired. But keep in mind, these kind of techniques can be powerful in targeted senses. If you see a current source in parallel with a resistor, you may be able to do a source transformation, which might help you reduce the number of equations in your nodal analysis, for example. So feel free to use these techniques, but just make a note to use them carefully. The real power of source transformation is going to come in the next segment, where we use it to find certain theorems to help us understand the distribution of power in circuits. So just kind of hold this into your back pocket until we get to that next module. Thanks.